believe most of you are watching this lecture on a video. Okay, I thought we could make it 3 weeks. I didn't think we would make it 1 week. But guys, we're gonna get through. We're going to make this as in a live class as possible. We're gonna make this as in a live class as possible. I don't know exactly how it's gonna work. I do think I'm going to move to a whiteboard. I'm gonna move to not a whiteboard app. Okay, it's gonna be the same kind of thing. It's just you guys are gonna see my face. Okay, you can actually see my mouth move. And I'm gonna move to a place where you have a whiteboard instead of a chalkboard because I think it's a little hard to read at times from the video. Also, if I can figure out how to do it, I'd love to have people zoom into the lecture and then me be able to pull down a screen and have you see your faces up on the screen. Even though it might be like the weatherman, who's looking over there and pretending like they're pointing at things, I'd be like, okay, what do you guys think? And then I'm looking at you like this instead of like this, but I still can see you. You could still ask questions. For me, that would be kind of like the best kind of live solution. Now we have Zoom Live now. They finally got the contract up and running. So like office hours are going to be, they're going to be live. Our first web is due when? Friday. Okay, the first thing I want you to do, and I want you guys, all the rest of you, there's like 10 of you in quarantine. I am so sorry. Okay, not in this class alone. In all my classes, there's 10 of you in quarantine. Okay, so this is our definition of our vectors. This is the definition of what it means to be vector on R3. Our working definition. It's going to be our class. So write it down. Scribe it down. So your job is to scribe this long-winded definition. I may have to actually make photos of you guys like for the baseball stadiums and put them in seats so that I can see you there, but I guess if I have the screen, then it's kind of like the Disney basketball arena. At least I could see you there, clapping as I do a slam dunk, which will never happen, both in math or in basketball. I always thought, I'm back when I was younger, a little taller than I am now, oh man, maybe one day I could be like Mike, okay, but no, this is what I've got jumping. That's what I got. It's never gotten any better than that. Okay, as you write, we'll read. Okay, we're defining what it means to be a vector. We're defining what it means to be a vector in R3, our working definition. Okay, so you guys help me out. Definition. Just say V of R3.
V of R3.
And how many people know that there's flashcards in the class? How many people know that there's flashcards? Okay, right now, pretty much what you have is the distance formula and the equation of a sphere. That's pretty much where we're at right now with our flashcards. Okay, this is just too much to write down as a flashcard. Okay, but how many on those flashcards? How many people looked at those 150? I mean, just opened it up and looked at it. How many times did you see the letter V, capital V on that thing? Wasn't it everywhere? Okay, this is that V. So if we're looking here, we're saying definition V of R3, the space of vectors on R3. That one, that's the most I can read right there. Okay, is the set of ordered triples. We got to actually describe what that means. Where we're saying that the vector A, say that,
The vector A
is a element of V denoted vector A equals our ordered triple A1, A2, A3. Now we don't want this to get confused with a point, so we don't want to use parentheses. We're using gators. Okay, we've got our gator mouse, our less than and greater than. We've got our gator symbols here. Okay, so we've got this ordered triple A1, A2, A3, and this is the key part. or A1, A2, and A3 are elements of the, or A1, A2, and A3 are elements of the, or A1, A2, A3 are elements of the real numbers, okay? So this is the first part of our definition. Now we kind of have to ask why. Why are we doing this? Because I don't think we really ask that quite often. Vectors, the idea of a vector really came along in the mid-1800s. Really, Euler, even back in the 1700s, kind of had the idea that coordinate algebra and coordinate geometry was not enough to model what was actually going on in the world around it. And I really think it was the discovery of electromagnetism that threw everything off. How are we going to actually talk about electric field in coordinate geometry with the algebra of the real numbers? Something had to give. Now, as a mathematician, I more relate to Grassmann. Grassmann was actually a high school teacher whose dad was an academic, whose dad was a professor. But he had this idea of marrying this algebra of the real numbers with geometry. What a sick idea. He's like, let's create a geometric algebra, an algebra for geometry. And what we learn in Calc 3 is just a small part of that. What we learn in Calc 3 is just a small part of that. Grassmannian algebras are really, really taking off in the 21st century. Grassmannian algebras are really taking off. Now, Hamilton, the guy who really talked about vectors, kind of gave us the basic idea. Gibbs is the one that we're talking about in Calc 3. Gibbs's butcher of Hamilton is what I teach you in Calc 3. But Hamilton more wanted to use vectors to talk about three-dimensional space, especially optics. Okay, so it was modeled by, this came out of a desire mathematically to marry algebra and geometry, and a desire to model things that were happening in the 1800s that they couldn't model with the algebra and geometry of the day. Does this make sense? I mean, a little bit. So I kind of want you throw yourself back in the 1800s. You're riding trains. Okay, you're going to ride trains home. Okay, you're not going to. And then we're not even talking about Madame Curie, who discovered radioactive stuff. I mean, that was suddenly a bigger game changer. We need bigger math. Okay, but back to where we were here. So we've got this idea. We're going to extend this idea of a number to a vector. Okay, and now I've got this vector A. So give me a vector. You're like, what the hell, Dr. Warren? Give me a vector. What would be a vector? Give me a vector. Well, let's think about it. It's got to be an ordered triple, where these three triples, these three people in the triple are real numbers. So give me a vector A, our first vector.
1, 2, 3.
1, 2, 3. Easy as. Sorry, I'm not Michael Jackson. Okay. Last thing you want to do is hear me say, is this a vector? Is this a vector? Is this a vector?
Yes.
Is it a vector? Does it meet the condition to be a vector? You're an ordered triple of three real numbers. Okay, but we're also going to have it subjected to an addition. Now I've got to ask you guys, and you guys in the video, because there's only like 10 of us here. Okay, the rest of you were there. Has addition been useful to us in our various disciplines? Has the addition of the real numbers been useful to us? Has it been, like 5 plus 2? Is that like knowing that is, some of you aren't even with me. 5 plus 2, knowing that is 7. Has that been useful?
Yes.
Okay, so let's assume that there's going to be some use in adding to, let's assume there's going to be some use in adding to vectors. So how do you get to be a vector again? An ordered triple of 3 real numbers. So give me another vector. Give me another vector. 4, 5, 6. Gotta love our creativity. We're like, okay. 1, let me think of another real number. How about 2? How about 3? And then we're like, how about 4, 5, 6? And that's what I would have said too. So now we're going to talk about an addition where we're going to add the vector A plus the vector B. And we're just assuming that it's going to be useful to do this. We just gotta assume it's going to be useful to do this. We gotta start asking ourselves, since we're creating this algebra for geometry, should the result be a vector? If you add a vector plus a vector, do we want the result to be a vector?
Yes.
Yes.
And you're like, okay, yeah, like that seems to make sense. Is a real number plus a real number? Okay, so let's make it a vector. That means you've got to be three. That means you've got to be in order triple of three real numbers. So what do you guys think? I mean, if you were back in the mid-1800s and it was your job to create this addition for vectors, what do you think you would make it? I mean, if you're just looking at that, what do you think you would make it? What would you make that first real number? 5? What would you make this second real number?
7.
And how about this third real number?
9.
9. I mean, isn't that what you do? Isn't that probably what a elementary school kid would probably do? Oh well, it's got to be 3 real numbers. Let's just add this guy and this guy. The first guy's there. Let's add the middle guys together, and let's add the other guys together. And that's exactly the thing that works the best. That's exactly the thing that works the best. And so our definition of adding 2 vectors is that we just add the components together and we get a vector. So a vector plus a vector is a vector plus a vector is a vector. Has multiplication been useful throughout time? Okay, so let's give us a multiplication. Now we're not quite ready for this nightmare yet. Vector A times the vector B, and everybody who's a physicist is like, what the hell is that? You know, they're like, and this is where Hamilton had a multiplication on vectors where you could do this. It was a quaternion multiplication. But what you needed was a scalar. You needed to accept that a scalar plus a vector, you don't even need to write this down, but you could because it's super cool. A scalar plus a vector is a quaternion. And he had a quaternion multiplication so that you could actually multiply vectors together. But people could not accept in the 1800s. Just even this idea of a vector was a lot for people to stretch. What's the point? Why aren't real numbers enough? I get that. Let alone to accept that a scalar plus what we'll find out is an oriented line segment is an object in itself. And multiplying them together. So Gibbs ended up saying it's too hard. It's too hard. Hamilton, what you're doing is too hard. People aren't going to understand it. Really, Gibbs came along about 50 years later. And it ended up costing, it's costing science and engineering today. The fact that we went with Gibbs and not Hamilton is costing science and engineering today. Now, gaming things, everything that was talking about motion is now realizing that you want to do it in quaternions, not with matrices. So what Gibbs did, A times B in vectors, in terms of Hamilton, ended up being this thing we'll call the dot product plus something with a cross product. And it ends up being a scalar plus a vector. It ends up being a scalar plus a vector. So what Gibbs did is he took Hamilton's product and broke it into 2 distinct products. But that's later in this chapter. It's called the dot product and the cross product. And yes, I agree, Gibbs, it's easier to understand. But you gave up freaking division to make it easier to understand. Can you divide 5 by 2? Yeah, there's a multiplicative inverse for 2. In quaternion space, there's multiplicative inverses. You can divide. Huge cost. A huge cost. But we're going to teach Gibbs's vectors. That's because that's the way it's always taught in 237. until I write my book, okay? I write my 237 book where I teach it in quaternions, okay, instead of with this. But back to when we're here. We're not ready to multiply vectors. Let's define an easier product we're going to call our scalar multiplication. It's going to be a real number times a. It's going to be a real number times a. It's going to be a real number times a vector. Okay, so give me a real number. Give me any real numbers. You're like, Dr. One, that's too hard. Give me a real number. What's your name right here? David, give me a real number. 7. So if I was doing 7 times a, where this is my vector a, it would be 7 times the order triple. 1, 2, 3. Easy as do, re, mi. Sorry. Easy as do, re, mi. 1, 2, 3. What will it be? Baby, you and me, girl. Come. What do you think? I mean, if you were just going to do it yourself, if you were going to define it, what would you think? Would you want it to be a vector? Yes. So let's make it a vector. You're like, okay, if you're a vector, then you're 3 real numbers. You're order triple 3. What would you make this one? What would you make that one? 7. What would you make this one? 14. What would you make this one? 21. Okay. So and that's exactly what it would be. The thing the elementary school kid comes up with is what works best. You just take the scalar and you multiply it times each of the components. Do you get a vector when it's all said and done? Is a real number times a real number a real number? And then, is there a commutativity? Dr. One, don't use such evil words. Is there a commutativity in the real numbers? Is it good that 2 times 5 is the same thing as 5 times 2? So I can actually, is alpha times a 1? The moment I make it Greek, people think they can't understand it. Oh, it's Greek. How many people have nightmares over that guy? Theta. Not damn theta. Omega. Physicists are just shaking in their feet right now. Okay, so I've got this real number alpha times a1. Is that the same thing as a1 times alpha? Is that the same thing as a1? And could I commute these guys? And not their sentence. I'm not commute. Commute means move them. I guess commute their sentence, move them. Okay. Commute, move them. And so we can say that this is the same thing as a times, we can say this is the same thing as a times alpha. This is the same thing times a times alpha. Okay, mathematicians, and I guess physicists and everybody else. Has it been good that we've had this sign in the real numbers? Has this been a useful thing to have? This relationship, has it been a useful thing to have? Could you imagine solving this without this? In fact, the word solve has equality in it. I mean, solve. Has it been useful to know when 2 real numbers are equal? Has it been useful to know when 2 real numbers are equal? So let's have an equality on this new number we're calling vectors. We're going to say, okay, A is equal to B. A is equal to B. Or in our ordered triple form, A1, A2, A3 equals B1, B2, B3. And so let's go back again. Imagine that I've got this vector, 3, 7, 5. We want to define an equality relation. How do you want to say that? That 2 vectors are equal? If you want to say 2 vectors are equal, what's your natural instinct say? Well, if we're going to say 2 vectors are equal, then this real number probably should be 3. This one should be 7, and this one should be 5. Now imagine somebody said, no, I don't like that. Why don't we just say as long as the numbers are the same? Like this would be equal. Would that kind of screw us up? I mean, might that create a little bit of havoc? So let's not do that. Let's just say 2 vectors are equal. Say that.
2 vectors are equal.
And let's give these guys inside, let's call them components. Say that. Components. 2 vectors are equal if their components are equal. 2 vectors are equal if their components are equal. If their ordered components are equal. Okay, so this is what we've got. This is our definition of vectors. We know that we're 3. We know that we're 3 real numbers. There's a addition. There's a scalar multiplication, and there's a equality relation. There's an equality relation. And then I dare say to everybody in the video, they're exactly what you would have defined them to be. They're exactly what you would have defined them to be. Okay, so now let's test some things out. Is there an identity element? Like Dr. Warren, I'm zoning. Stand up, stand up, stand up, stand up, stand up. There's not enough people in here for this thing. Let's stand up. Stretch. This is when I'd have you guys, if we didn't wear a mask, I'd have you smack your face around. I'd have you do just anything to wake you up. Pound your head. And you guys better be doing this in the video. And you guys, when you go home, and I tell you to stand up. Okay, smack your head. I know what I'm doing. Doesn't look like it. Okay, let's sit back down. Don't show your parents or anybody these videos. But take notes just like you're in the room. Take notes just like you're in the room. And it's probably as bad as it sounds is to do it in a long stretch. Not like, okay, I'm going to watch you for 30 seconds, turn it off, and go drink a beer. Okay, I'm filming this, okay? Go drink water, okay? And then I'm going to come back and watch Dr. Warren, okay? You know, it's probably best to just do the hour, maybe to break me into 2 45 minutes. Because I couldn't stand myself for an hour and 15 minutes. I'm always like the one, I'm like, I don't know how my wife does it. I really don't know how she puts up with me. I really don't. I want to get away from me half the time. My attitude can be so bad when I'm driving. I don't want to be around this human being. But I have no choice. I'm stuck with me. But somehow she manages to get through year to year. Okay. Our identity element in the real numbers is 0. Because it doesn't, under the operation of addition, say that. It doesn't change the identity of the person that's operating on. 5 plus 0 is 5. Now we've got this brand new idea of a number we're calling a vector. Let's just, give me a vector. I know this is hard. Dr. Warren is just too open. I can't do it. Give me a vector. 10, 4, 6. Could I make that a pi? Could 6 be a pi and still be could it be a vector if I made it a pi? Like, Dr. Warren, what are you talking about? Are you talking about this kind of pi? Or are you talking about this kind of pi? So as long as it's the second, then it would be a vector. Is there an identity vector that wouldn't change your vector's identity under this new addition we defined? Is there an ordered triple that wouldn't change this vector's identity? Write down what you think it is. If you had to take a guess, write down what you think it is. Now in the US, we hate being wrong. We're somehow trained not to be wrong. That being wrong is bad. When you're learning something new, aren't you always going to be wrong at some point? Yes. I mean, anytime you're learning a sport, you're not Michael Jordan coming out of the blocks. How many people have bled learning a sport? Yeah, I mean, so yeah, Cameron, if you're writing that thing, I know you've bled. What do you guys think? I need 3 real numbers. I need 3 real numbers that wouldn't change this identity, this guy's identity. What would you have? 0, 0, 0. And we call this our identity vector. We should probably give it a specific symbol. What do you guys think? What do you want to use?
0 with an X.
Yeah, we could use a 0 like this, but I don't like doing that. I'm lazy, so I like that. It means the same thing. It's just bold 0. It's just bold 0. So we call this our identity vector. And a plus 0 is a. And 0 plus a. 0 plus a is a. Now let's make a proof. You're like, no, Dr. Warren, let's not make a proof. Let's not make a proof. No, let's make a proof. Do you guys think this is true, first of all? Do you guys think this is true or false? That a plus b, the vector a plus b, would be the same vector as b plus a. Do you think that should be true? So let's try to prove it by what we have. Math is proof. Math is proof. So I'm going to start with this. I'm given A and B are in B. And if you look at your flashcards, they're a lie. Read this to me. The vector A and the vector B are elements of my vector space, or elements of my space of vectors. Then A plus B is equal to an ordered triple A1, A2, A3. Okay, now for you at home, is equal to plus another ordered triple, and what did you say? What did you say? B1, B2, and B3. I even heard you talk through the camera to me. B1, 2, B2. And now let's give our justification. We've made a move. Let's give our justification. It's the definition of our vector space. It's the definition of our vector space. You get to be a vector if you're an ordered triple of 3 real numbers. But this is equal to what vector? I mean, if you're thinking logically, this is equal to what vector? This is equal to what vector? You guys defined it. How do you add vectors? I mean, by our addition. I mean, if you're going over here, my justification is going to be this thing I'm going to call V plus. How do we define the vector addition? What do we do? Add each of the components. So we'd have the first real number would be A1 plus B1. The second real number would be
A2 plus B2.
the third real number would be
A3 plus B3.
and my justification is vector addition. Now it gets a little bit complicated. Now you're like, what do I do now? Like I've kind of got here, I'm there, okay, I get this is what a vector is. This is my vector addition. And like, what do I do? Well, what are we trying to show? We're trying to show the vector A plus the vector B is equal to the vector B plus the vector A. And we're at A1 plus B1, A2 plus B2, A3 plus B3. What do you guys think? You're like, well, Dr. Warren, those are real numbers. Is there a commutative property? On the real numbers? So you guys at home and you guys here, write down what you think the next line in this argument is going to be. What do you think the next line in this argument is going to be? And this is maybe the critical one. I don't want to be wrong, Dr. Warren. No, go ahead. I give you freedom to be wrong. It's good to be wrong as long as you're learning. And now, just hold it up so other people can see it. Now, this is going to be a little harder at home when you're watching it on stupid video. So, Robert, what do you got for me, man?
I had B1 plus A1, B2 plus A2, and B3 plus A3 by commutative addition.
Perfect, Robert. That is awesome. Yeah, and that's by my commutative property of addition. And this is on the real numbers. I mean, that's what we're using there. So I've got this real number plus this real number, this real number plus this real number, and this real number plus this real number. But this is the same thing as B1, B2, B3, plus A1, A2, A3, And what are we using there? What are we using there, guys? What are we using there? How can we say that this line is the same as that line? What are we using to say that this line is the same as that line? Well, like Dr. Warren, it's kind of like what were you doing from here? We were here and we went to there. Now we're just kind of throwing it in reverse, kind of like we're in Fast and the Furious 6. I'm driving. Throw it in reverse. Skid around. And we're like, okay, we're really using our vector addition. We're really using our vector addition there. And then this would be equal to B plus A. This would be equal to B plus A. By again, the addition of our vector space on R3. The addition of our vector space on R3. And so here's an argument to show that A plus B, the vector A plus the vector B is equal to the vector A plus the vector B is equal to the vector A plus the vector B. So I gotta ask, if you're looking at this, would it be bad if these weren't the same? Might that screw us pretty badly? If this was not the same as this. If you added 2 plus 3 first, and then you added 7. Okay? Or if you added 2, and then you added 3 plus 7. If you didn't get the same number out, would that be bad? Now think a computer's got to do this in some kind of order. It's either got to do this one and then add that one, or it's got to do this one and then add that one. Would it be bad if you didn't get the same bits flying out in that number storage? Would that screw up NASA? Do you guys think we could show this? Do you guys think you could show that? Do you think we could go through the same kind of steps that we did here for the commutative property to show that our vector under the addition also has an associative property? It's going to rely really heavily on the associative property of the, real numbers. It's going to rely really heavily on the associative property of real numbers. Okay, stand up again, What time is class end? 11, take out anything you have that sells time. Because that clock up there doesn't. That clock up there that's supposed to be here to help us says it's 12:05. What time is it?
10:41.
What?
10:41. Sit back down. What are you doing, Dr. Warren? I'm believing that we're all coming back in October. That I'm going to see you guys again. Because I can't teach to a camera for the entire semester. Okay, sorry. I know you needed a break. I know you're not. Has subtraction been useful? Let me just ask you. Have you used subtraction ever in your life?
Yes.
But we never really, like, a lot of us, we would say this means 3, okay, no. We say this is 5 minus 2. And I'm like, well, what does that really mean in the real numbers? And you're like, it's 5 minus 2. What aren't you understanding, Dr. Warren? No, I mean, what does that really mean in the real numbers? You're like, well, you got 5, and you take away 2. I'm like, oh no, as far as the real numbers are concerned, what does that mean? You're like, what aren't you getting? You got 5 damn things, you take away 2, you got 3. But no, guys, we can't do that. When we're talking about an algebra, there's got to be something concrete. Subtraction is not really an operation. It's really addition. And a lot of people, it messes up kids because they don't think about it that way. It's really addition. And this is where, for 2, one of the properties of the real numbers is there has to be another real number that'll get you back to the additive identity. It's called the additive inverse. What real number plus 2 is the additive identity element 0? Negative 2. The reason we call it negative 2 is we want to distinguish it from this. It's the additive inverse of 2. So when we talk about 5 minus 2, we really are meaning 5 plus negative 2. The real number you get by adding 2's additive inverse. Now I'm going to ask, do our vectors have additive inverses?
Of course.
So I'm going to give me an A. And don't say A, okay. Give me an A, any A. Give me an A. Give me a vector.
6.
6, okay.
1.
1, okay, but at least we're not going straight up.
9.
9. Vector or not? Vector or not? Vector or not?
Nope.
Now I'm going to ask, does this idea of an additive inverse, we got this new vector addition, does this idea of an additive inverse, a negative A, what do you guys have? Does it seem like it should make sense? What do you think would be something that we could add to A? Is there a vector that we could add to A and get our 0 vector? Is there a vector that we could add to A and get our 0 vector? What do you guys think? Yes or no? What would the additive inverse be?
Negative 6, negative 1.
Negative 6, negative 1, negative 9. By our vector addition, would this end up being 0, 0, 0, our 0 vector? So in general, if A is equal to A1, A2, A3, what's minus A? What's our additive inverse going to be? What's our additive inverse going to be? What's our additive inverse going to be?
Negative A1.
Negative A1, and then negative,
A3.
and negative A3, negative A3. Oh, crap. Sorry. So when we talk about A minus B, when we talk about A minus B, we really mean A plus, negative B. I'll get out of the way. I promise. A1, this is by the definition of being a vector, you have this order triple. This is the additive inverse of B. Now by our addition, how do we add vectors? Component to component, so this would be A1 plus negative B1, A2 plus negative B2, A3, I'm talking to a mask, A3 plus negative B3, but this is the same thing as A1, this is the same thing as A1
Minus B1.
A1 minus B1, A2 minus B2, and A3 minus B3. Okay, stand up again. I need you, because we're not in shape.
So is it still supposed to go with like the steps? Or that's supposed to still be the first?
No, I'm not making any proof there, Cameron. That's a good question. Other questions? How are we gonna survive? Is that maybe the question? How are we gonna do this Calc 3 online for a while? Where we are? I don't know what Friday's gonna be yet. I just don't know. I'll figure it out between today and tomorrow. But at least I'll have met my A team and my Z team twice. Ugh. Okay, sit back down. I guess maybe, let me just do this real quick. Let's talk about the scalar multiplication for a minute. 1 times a, what do you think it is equal to? 1 times a, what do you think it is equal to? What do you think it is? 1 times the vector a, what do you think you could show it's equal to? It's equal to a, yeah. And you're gonna use the multiplicative identity of the real numbers. 1 times a1. 1 times a1. 1 times a1. 1 times a2. 1 times a3. You're gonna get the same vector. You're gonna get the same vector. How about the scalar 0 times the vector a? The scalar 0 times the vector a. It's equal to 0, but is it the 0 real number, or is it the 0 vector? It's the 0 vector. So you're like, you gotta be careful here. 0 times a is 0, but it's not the real number 0, it's the vector 0. It's the vector 0. All right. Can I erase all this? You guys at home, I just don't have much of it. Now I'm gonna go back and I'm gonna ask the same question. Why? Why are we doing this? Yeah, it's kind of okay, Dr. Warren. Yeah, I get it. It's kind of fun. You have this thing you're calling a vector. You define an addition. We saw it's commutative. We saw it's associative. It has added inverses, have an additive identity, multiplicative identity. That's all interesting mathematically, but why? Well, remember what Grassmann wanted. Grassmann wanted to marry algebra to geometry. And you're like, how can we do this? Well, we could work in 3-dimensional space. We could talk about it in 3-dimensional space. We could talk about a vector plus a vector in 3-dimensional space. But guys, if we can't understand it in the plane, is there any way we're going to understand it in 3-dimensional space? So let's start geometrically a little bit easier. Let's start, instead of in 3-dimensional space, just with 2-dimensional space. So let's go back to our friendly, where we're nice and comfortable from high school, XY. Okay, now in 2-dimensional space, how many real numbers will I need for my vector? In 2-dimensional space, how many real numbers will I need? So let's go ahead and just, let's get some real vectors on here. In 2-dimensional space, give me a vector. In 2-dimensional space, give me a vector.
3, 7.
3, 7. Now let's make this one. Make this one
2, 4.
2, 4. Okay, true or false, vectors. These would be vectors. By the definition of vectors, they'd be vectors. Okay, could you add them together? If you add them together, would you get another vector? So find that vector, find that vector. Give me a reasonably small scalar. Give me a reasonably small real number. 2. Could you multiply 2 times a? Could you multiply 2 times a? And would you get another vector? Find that too. Find that. Find out what that vector is. Okay, so what did you guys get here? What did you get here? I should make you cheat and look around, I'm looking at time. Okay, what would you get here? What would you get here? Get 5. How many people got that? How many people got that? How many people at home got that? If you just pause me right now, okay, I'm pissed. 5, 11. How about this vector? What'd you get for that vector? What'd you get for that vector? Really, you coming up using your own operation, what would you find that to be? 6, 14. And you're kind of like, okay, well, what does this mean geometrically? And I gotta imagine that somebody had to sit for some time in the 1800s and be thinking, I mean, like, I like this idea. They look a lot like, if I'm just thinking about it, it looks a lot like points. So I gotta imagine that's probably where they started. They're like, okay, well, if I'm thinking about this, I know this isn't the same as this. And this would be like 5, 11. I gotta imagine that what they did was just, let's plot some points. We would go, this point we'd go over 3. We'd go up. 7. So that'd be that point. This point we would go over 2 up. In this third point, we go over 5. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be a little bit hard to see with the way we've drawn it there, but then I gotta imagine what they did is they kind of sat down again and were like, okay, what does this mean? And like, well, we're saying a point plus a point is a point plus a point is a point. But we're like, points have been failing us. Points have been failing us. And I gotta think somebody said, well, let's, instead of just thinking as points, let's think of them as line segments. Let's think of them as line segments. And like, sit back down again. Well, which line segment? What would be the line segment 2, 4? If that's a vector, and I'm thinking about this vector as being a line segment, what would be the line segment 2, 4? There's a bunch of, how many people realize there's a bunch of line segments in a plane? I mean, go ahead. You're like, okay, what would be the line segment 2, 4? And I gotta think somebody said, well, if you're explaining to a little kid how to get to the point 2, 4, you'd say, okay, you start at the origin and you go over, it's just like battleship, you go over 2, up 4, hit. Okay? I got to imagine, they're like, okay, well, let's just make that line segment. Well, think of this as A. No, that's B. And this is where my vectors have got. This would be the vector A. And this would be the vector C. At least in this idea that we're moving. Now we know that A plus B is, by the way you found it, A plus B is C. But does A plus B equal B plus A? Does A plus B equal B plus A? So this would be the same thing as B plus A. Now you're looking at these 3 line segments and you're like, so a line segment plus a line segment is going to be a line, this line segment plus this line segment's got to be equal to that line segment. And this line segment plus this line segment is the same line segment by our algebra that we defined it. Like, well, what's the geometry of this? Now, I can imagine they stared at it for some time. You're like, okay, A plus B is C. I can imagine them like, I mean, like, well then, I mean, if this is B, I keep the direction and the length the same, and I kind of put it up here. This would be like A plus B, but this would be, oh, this is where, oh. But this would be like B plus A. And I'm gonna redraw the picture. But just with two different vectors. I just want to have it a little bit more. Imagine that this is the vector A. This is the vector B. And this is the vector C. Then we're saying that A plus B is C, and B plus A is C. And then I got to imagine like somebody would just like vomit it into their mask, okay? And just imagine that there was a pandemic going through somewhere. They vomited into their mask because they're like, oh crap, this isn't going to work at all. Let's just dump this idea right now. Let's just stop. Because that would mean then that this is the vector A. This line segment's the vector A. But also, that line segment is the vector A. Like, oh, you gotta freaking be kidding me. This is A and this is A. We have this algebra now, but it's forcing this to be A and this to be, and this to be B and this to be B. You're like, oh crap, it could get worse. Imagine that this is a vector D, and I added on, oh gosh, it's getting much worse, Dr. Warren, focus. Imagine that I've got this vector D, and I also add on A, we'd have a new vector. I can't even stop myself from putting the arrows on it. Okay, so we got this. We got this line segment plus this line segment. There we go. Which would also be the vector A. I mean, like for example, if you came over here and I said, okay, D is equal to 15, 21, and I did D plus A. If I did D plus A, what would you get? Using the algebra, what would you get? You have 15, 21, and you're going to add on A. What do you get?
15, 28.
You get another line segment. But geometrically, now suddenly we're out here. And then I imagine they had to just sit there and be like, we should quit. Or let's go ahead. Let's just go ahead. Let's just accept. A vector geometrically is going to be something where what matters is its orientation and its length. What matters is its orientation and its length. And if we jump up to 3 dimensions, it's the same thing. It's orientation and its length. This is the green vector. This is the green vector. This is also 6 feet away. This is also the green vector. The algebra is telling us you cannot say this is the green vector by itself. No matter where it's at in 3-dimensional space, as long as it has the same orientation and the same length, it's the same vector. I'm surprised they didn't quit then. Because that's such a jump. It's a jump today. When you first learn about vectors, then like, okay, well this is the vector A and this is vector A. What? Remember the first time you learned about that, you're like, what? What? It's not just this one? This one with its butt at the origin. This one we call it the direction vector. Say that. We kind of pull out from all the rest of them. We call it the direction vector. But it gets worse. You're like, no, Dr. Warren, it can't get any worse. Let's plot A. We go over 3 up 7. So this is like the vector A. This is the point 3, 7. Say that.
3, 7.
This is the point 3, 7. This is the vector 3, 7. This is the point.
3, 7.
This is the vector 3, 7. Now let's look at this vector. I don't have anything better. I'm going to use an ice cream cone. Let's look at the vector -3, -7. Let's look at the vector -3, -7. Is it a vector? Is it a vector? Is it real numbers? Is it real numbers? Plot that vector. Okay, so what would you guys do if you're plotting the vector? If we're plotting this vector, what line segment would we use? What line segment would we use? We'd go over 3. We'd go. My first class, I plotted it wrong. I don't know what I was doing. I plotted it wrong. I was an idiot. I'm so glad I'm not filming this one. 1, 2, 3, 4, 5, 6, 7. And so this would be the vector minus it. So this is the vector A, this is the vector minus it. And I imagine at their time they're like, oh crap. Because we just said, this is the blue vector, but this is also the, no matter where I move it, as long as it has the same length and the same orientation in 3-dimensional space, it's the same damn vector. And they're like, well, this vector's this long, and this vector's this long. This vector's oriented in 3-dimensional space this way, and this vector's oriented in 3-dimensional space that way. They gotta be the same vector. And you're like, but does the vector -3 -7 equal the vector 3, 7? No. You said A1 equals A1, B1 equals B1. Oh my gosh. You gotta be kidding me. There's an orientation. So we put an arrowhead. Now again, imagine what a leap this was for human beings at this point. Not only are we talking about line segments, adding line segments, but our vectors have to have a orientation. Where we start to where we end, we put an arrow. We put an arrow. Later on in physics, does it matter if the force going in the exact same direction pushes this way or pushes that way? Does that make a difference? And this is the algebra we use to model it. Has it been useful? Has it been useful? Okay. So when we're adding vectors, we do this thing called the head to tail rule. It sounds so stupid. What's it? So if I've got in two-dimensional space, I have this vector A, and I've got this vector B. We could go and find the points. Then we could add the points together, get our other vector. But the way that we can do it visually, geometrically, is we take A plus B, we take the butt of B and put it on the head of A. It's the same vector. It's the same vector. We got an orientation, and A plus B is C, but B plus, we take the butt of A, we put it on the head of B, is equal to B plus A, Do you get the same vector? Say supercalifragilisticexpialidocious. At home, say supercalifragilisticexpialidocious. Why, Dr. Warren? Just because I need you to wake up. We have 10 minutes. Okay, so now I've got my vector blue in three-dimensional space. I've got my vector blue. And I've got my vector mustache. I've got my vector blue and I've got my vector mustache. How do I find my vector blue plus mustache? This stays the same direction. And I go there. Oh, this is when I wish I was an octopus. So now I'm there. And then this green vector would be blue plus mustache. Would it also be mustache plus blue? So if I go back and put my direction vectors down, I don't think I can do this. This is where it'd be so easy. I mean, get the hell up here and help me. But now I'm like, okay, I can't even help. Do you guys see that at home? Isn't that a beautiful visualization of it? Isn't that beautiful? Aren't you learning so much by this? Do you see how it extends naturally to three-dimensional space? Okay, so now let's talk about subtraction. No, Dr. Moore, let's not. My brain's still kind of spinning from, oh, this is the green vector, and this is the green vector. But this ain't the green vector. That's the negative of the green vector. Now, you guys, how many people have had physics before? How many people have had a class in physics? How many people have heard vectors before? Has anybody in here talked about vectors before? I mean, if you're thinking about it, it's kind of natural to you. But imagine when it was birthed. How hard, imagine when they're like, oh, this and that, let's quit. I mean, you had to be on the edge of quitting. I wonder how many great inventions were right on the edge of quitting. I'm wondering how many times Einstein was like, oh crap, it's not worth it. I quit. And then he's a patent clerk, and I'm so bored out of my skull. Let me stare out this window and just do these thought imaginations out there. I got these two trains. Okay, well, no. Let's talk about vector. Let's not talk about relativity. Let's talk about subtraction. I want to talk about, I've got a vector A, and I want to subtract B. This really means A plus negative B. If you add two vectors, do you get a vector? By the way, we defined it. If you add two vectors, do you get a vector? Okay, so let's call this C. Now again, if I can't understand it in the plane, I'm screwed in three-dimensional space. So again, maybe I'll call this A. I'll call that B. Now, how many people are pretty comfortable they can find A plus B visually in our new geometry? Applying this algebra to geometry. Applying this algebra to, what did I want to say? Geometry. How many people think they could find the vector A plus B? Okay, but now I'm not asking for the vector A plus B, I'm asking for the I'm asking for the vector. How do you guys learn anything from me? And I actually think it's not bad until I watch it. And then I'm like, oh my gosh. It's like me playing sports. I think I'm in a basketball court and I'm out there and I feel like I'm looking cool. I feel like I made that move and I want to like be like, did you guys see that? Did you see that? But then you see a video and you're like, oh my gosh, that's the way it really looks? That's the way it really looks? That looks so much cooler. Can you actually imagine being Michael Jordan? Because Michael Jordan, it looked so freaking cool. What did it look like in his head? Like right now, I'm up here, I've got my big eyes, I'm looking at you, I see the board up close. I think you guys see it that close, I'm bigger than life. And then I look at the video and I'm just this little tiny guy and there's this little tiny print, and this is what you guys are taking in. Okay. Let's talk about the vector A minus B geometrically. Like, ooh. Well, I do know that A minus B, by the way we define the algebra, is the same thing as A plus negative B. Now, where's the vector negative B? Where's the vector negative B? What would you guys have? I mean, if we're drawing the direction vector, like Dr. One, there's infinitely many. I know. But if you're drawing the direction vector, negative B, what would you do? What would you do? You'd go back, same orientation, same line segment, just a opposite direction. Okay, so this would be like my negative B. Now you guys would be like, Dr. Warren, I kind of think I understand. I feel like I can understand that how to do addition. So if I was doing vector addition, A plus negative B, I would take minus B and go, add it onto the head of A. So let's do that. Pretend like we stop my coordinate plane. I would take this guy and go, woo! I don't know why I think the visual helps. The sounds, woo! So this is also minus B. I know it pisses us off. Is this minus B and is this minus B? Okay, then this vector would be C, which is like my A plus minus B, which is also the vector A minus B. It's just a notation. You're like, okay, crap, Dr. Warren. This is the way you want me to do this. You want me to think of A, then you want me to reverse it here, and then you want me to add it on there, and then you want me to draw that vector. That's the vector A minus B. And this is where it actually comes to our advantage. The fact that the vectors are the vectors everywhere in three-dimensional space. Because this vector A minus B, if I take this guy, and I go, whoops, if I do that, would that also be the same vector? If I take this vector and go like that, would that be the same vector? And so you see that geometrically, the vector A minus B is the vector that connects the two heads of the vector. Is the vector that connects the two heads of the vector. And you're like, well, Dr. Warren, which direction does it go in? Well, it goes in the direction where the result was. It goes in the direction where what you were subtracting from. It goes in the direction of what you were subtracting from. So if I was looking at green vector, if I was looking at the green vector minus the blue vector in three-dimensional space, it would be the vector that, green vector minus blue vector would be the vector that connects the two endpoints. Where would the butt be? Where would the butt be? At the, this is, okay, so I don't know if I can do this like this, I'm not even sure how. Okay. It'd be that vector, How about blue vector minus green vector? How about blue vector minus green vector? Somebody looks like you only have a pulse right
Flip
now.
the mustache.
Oh my gosh, do you have coronavirus? That's not even a joke, is it? It's not even close to being politically correct. Okay. All right. How many people have a better sense of what a vector is? Right now, our two operations are we have a vector addition and we have a scalar multiplication. Let me just end with this, then I'm freeing you. I mean, if you just had to guess, if you have A and you had 2 times A, if you had A and you had 2 times A, 2 times A would be the vector 6. If this is A, then this would be the vector 6, 14. So you go over 6, you go 14. Do you see how it lies in the exact same vector? It's the same vector, it's just it's stretched twice. And does it make sense why we call it scalar multiplication? So a scalar just stretches. You multiply times a negative scalar, it doesn't just stretch it, it flips it around. Guys, I'm so sorry. I'm so sorry that you're not just coming back here on Monday. That already sounded absurd. Monday, not Friday. Okay. Listen, we're going to make this work. We're going to make this work. Thanks for coming and playing today. Thanks for coming and playing today. And I'm believing, guys, I'm going to see you in October. I'm believing. I'm an optimist. I'm going to see you in October. Yeah, I made that. Just PVC pipe and duct tape. I'm like, my kids can't, like when I go on the board, I'm like, they can't see
Better
that.
than a roller.
That's nice.
Thanks for letting me come.
Oh, no, thanks, guys.
We'll see you Friday at 2 o'clock.
Thank you.
Yeah.
Thanks, what's your name? Brett?
Yeah.
Okay, nice to see you.
Thank you.
And you are Caitlin and David. Bridget, thanks, Bridget, thanks for coming and playing. I bet you thought I forgot about you. I bet you did. I bet you thought I forgot about you. No, these are like the credits at the end of the Marvel movie, okay? We still have so much more to do. Be ready for Calc 3 Part Online.